Hello everyone, today I'm happy to be here to give a presentation of my research about adversarial audio, a new information handling method. And here is the overview of my presentation. First, I will introduce the information heading. It means use human's perceptual redundancy for digital signals and hide secret information into the carrier. Generally, the carrier can be divided into three types: images, audios, and videos. And why audio is chosen to be researched? Because it's an important medium in people's daily life, and it have a good imperceptibility in the transmission of information. In the meantime, it can provide a lot of redundant space for hiding information. So we choose audio to do the information heading. And then we will introduce the preliminary knowledge, the adversarial examples. For example, the left is a original signal and the middle is the ASR model. The ASR means the automatic speech recognition model. And when the audio signal input into the ASR model, the model will output the corresponding text. Here is it was the best of times, it was the worst of times. And then we will add the perturbation into the original speech signal. Then we get an adversarial speech audio. Then we input the adversarial example into the same ASR model. It will output a different result. Here is it's a choose universally acknowledged data single. And by inputting a small perturbation to the original signal, the automatic speech recognition model can output any desired or other misclassification with high confidence. And this phenomenon that leads to the wrong output is called adversarial examples. And then here is our proposed method. This is the process of embedding hidden information into audios. First, we will have an original audio signal X and the target hidden text. The target hidden text means the information that you want to hide into the X. Then we input this into the ASR model, and we will get a text that the original audio signal means. And it's obvious that the recognized text and the target hidden text is different. So we need another parameter, delta perturbation. The delta will be added into the X to make the ASR model to recognize the result to approximate to the target hidden text. So it's an iteration step that's to training and updating the perturbation to make the delta plus X to get the stereo audio signal X prime to make the ASR model to recognize the X prime to be the target hidden text. Here's the algorithm of information embedding. And the input is the original audio signal X and the hidden text T. The output is the stego audio signal X prime. The initialized process will have three parameters, the delta, tau, and m. The delta is an initial zero array with the same shape of X, and tau is the threshold of delta. And the n is the max iteration times. First, we will give the initial X prime by plus the X and delta. Then we will start the iteration steps. In the iteration steps, first we will calculate the loss. The loss L indicates the magnitude of the city-state loss between the recalculation results of X prime and the target text T. And then we will use the gradient optimizer, a damp optimizer to calculate the L and the delta to update the delta. Then the delta, after the delta is updated, we will apply a clip function to the delta with the threshold of tau. The tau means to make the delta between the threshold, and then we will reduce the tau to make the delta to be smaller. And then when it reaches the max iteration times n, we will output and return the last best result that the C X prime equals to T. And here is the iteration function, like the algorithm. And this is the experimental setup. The iteration times n we set to be 500, and the threshold tau is set to be 3,000. And then this is the process of extracting hidden information from stego audios. From the embedding method above, we can easily to know the stego audio signal input into the Adversarial model. It will directly output the target hidden text that what we want. So the process of extracting is a simple process that we just input this signal to the same Adversarial model before. It will output the result. And here are some audio examples we generated. The example 1. The first audio is the original audio signal we can hear.
Thomas went to war.
Thomas went to war. And the second is the adversarial audio we generated, and we can hear.
Thomas went to war.
And we hear is still Thomas went to war, but the recognized result is close the door. And the example 2.
Some of our biggest clients are affected.
Some of our biggest clients are affected, and the adversarial audio.
Some of our biggest clients are affected.
The recognized result is call the police. And the example 3.
I'm smoking too much.
I'm smoking too much. The original is this, and the adversarial audio.
I'm smoking too much.
It can be recognized as see you at 5 p.m. So from these 3 examples, we can hear that two audios are hardly to be recognized. There are differences between them. So we have do some evaluations for our research. There are 4 indicators are used to evaluate our method, and we have generated 100 stereo audios. This is the 100 audio. We divided into 10 groups, and every group will have a different heading information. For example, the G1, group G1, will had be quiet, and sing louder will be heading into the G2 group. And the 4 indicators are heading capacity, imperceptibility, robustness, and security. The heading capacity of our stereo audios, the result is like this. We use character per second to evaluate our heading capacity because we just directly heading a whole sentence into the audio. So we use character per second to evaluate our method, and the result is the average heading capacity is 48 CPS. It means every second audio we can add 48 characters into it. So it's quite a good result. And then the imperceptibility. We used PSQ to evaluate our method. The PSQ means the perceptual evaluation of speech quality. In general, the score of PSQ is between 1 and 4.5. The worse the speech quality, the lower the score. And we evaluate the imperceptibility by comparing with a recently proposed audio information heading method 4. And from the figure, we can see the blue one is our method, and the orange one is the method in reference 4. And the average PSQ value of our proposed method is 3.598. While the method in the latest research method is 2.351, which means that our method has better imperceptibility. And then is the robustness. We have applied 4 signal processing methods to our generated audios. They are white Gauss noise, resampling, lower filter, and echo interference. And according to the results, we can say that the stereo audio signals have lost their hidden text after being processed by the full text, except the resampling. It will still have the 46% to reserve the hidden text. And so the robustness is not very well about our method. And then the last indicator is security. According to the result, we can say the deep speech 0.1.0 version is the model that we choose as our private model that we train our generated audios using this. And the 4 other models are different with the Interspeech 0.10 version. So we can say only the private model can extract the hidden information, and other models cannot extract data, the information we hide into the audios. So the security is very high. Only the model we have privately can extract the information. And last, the conclusion. The advantage of our methods is high hiding capacity, good imperceptibility, and high security. And the disadvantage is the robustness is quite low. So our future plan is to research how to improve the robustness of sticker audios. And that's my whole presentation. Thank you.